Okay, let's consider next the work done on a test charge Q dash moving in the electric field caused by a single stationary point charge Q. Such a force field is clearly not uniform, and we have to integrate to calculate the work done on Q dash. We first calculate the work done on Q dash during a placement along the radial line from point A to point B in this diagram. So we're going to calculate the work done going from A to B in this diagram here. So we can see that we have the radial line here is depicted as RA from Q to A, and then from Q to Q dashed, obviously it's R, and from Q to the final point is RB. We'll introduce a unit vector R hat pointing from A to B. So this is R hat here pointing from A to B. The component of displacement in this direction is just dr, and the component of force on Q dash in this direction is F equals 1 over 4 pi epsilon naught Q dash R2. So that's the force between Q dash and Q is given by this equation. R hat is a unit vector from A to B. So what we can say is the work done by the force on Q as it moves from RA to RB is given by this equation here. So we're integrating, so what we've got is the work, as you know, is the force times the distance, but we want the work over the distance from A to B. So that is we'll just form the integral there, and then we'll use the force, which is simply Coulomb's law, and we'll insert that here, and we end up with this equation. Now, of course, when we do the integration, we'll end up with the fact that the work going from A to B is pulling out, after the integration, if you just pull out these parts, you're just basically integrating 1 over r squared, and you end up with, if you do that integration, it's very simple, you end up with this equation. Thus the work done for this particular path depends only on the endpoints. We have not yet proved that the work is same for all possible paths from A to B, so this integration does not depend on the path we take, it's just on the two endpoints. That's the important point about the work here. To prove that, we consider a more general displacement in which A and B do not lie in the same radial line, as in this diagram here. So we've got A, you can see that there's a line here, it's quite arbitrary, and it goes from A to B here. To find the work done by the field in the displacement from A to point B, we must now use the general definition of work given by W equals the component, this is F cosine theta, which is the component along the small displacement dl, which is this displacement here, and that is simply, and remember that F cosine theta is the same as the force vector dotted with the displacement vector dl. This is basically the dot product of two vectors. It's the same as F cosine theta, remember the dot product. Now also remember F cosine theta is component of F parallel to dl, that's lying in this dl direction. We can also see that cosine theta dl, which is this amount here, that's cosine theta dl. Now that's the small displacement dr going from this point Q dash to this little displacement dl. That's the displacement in the radial direction. What we're saying is the work done during a small displacement dl depends only on the change dr in the distance r between the charges, which is the radial component of the displacement. So in any displacement in which r does not change, f and dl, so the vectors f and dl are perpendicular, because obviously if r does not change, then you've got the same electric field value all the way around. If r does not change, it's exactly the same. So you can see here that f and dl are perpendicular. In other words, cosine 90 equals 0, so f dot dl equals 0, and no work done. So that proves that there's no work done if the radial distance is the same between 2 points. Okay, Thus equation 1 is valid even for the more general case. So although that's a bit wordy, what we're saying is that proves that in the general case that the work going from A to B is completely independent of what type of path. We can take any kind of path we like. It's completely independent because of the fact that, you know, if the radial distance is the same, then you're not doing any work moving from one area that's got the same radial distance as the other point that's in the same radial distance from this charge. So there's no work done. The only work that's done is when you're going up or down in this path, which is given by obviously this equation. In my notes here, I'll just repeat. It says, thus equation 1, this equation, gives the work done by the field even for this more general displacement. The work is the same for any path between these points, or between any pair of points at distances RA and RB from the charge Q. If the test charge returns from B to A along any path, the work done by the electric field is the negative of that done in the displacement from A to B. So the total work done during a loop displacement, so if we go from A to B and then somehow come in a different path going back to A, then obviously we're returning back to the potential energy we had. So so basically the total work done during a loop displacement returning to the starting point is obviously 0. So when we loop back, we're back to where we were, so there's been no work done. Comparing this equation with this equation here, we can see that the term q 4 pi epsilon naught over RA is the potential energy given to UA when Q dash is at the point A at distance RA from Q, and similarly Q dash 4 pi epsilon naught RB is the potential energy that we're given capital UB when it is at point B at distance RB from Q, from this Q, okay? Thus the potential energy U of test charge Q dash at any distance R from charge Q is given by this general equation. So the potential energy of a test charge Q dash at a point A in this diagram due to a collection of charges Q1, Q2, Q3 and so on at distances R1, R2, R3 and so on from the test charge Q dash is given by, so we just sum them all up basically, and we have this general equation here for a collection of charges.